here? Oh, most common question. That's one, right? Those of you who are in Bay Math League, in math team, this was one of the question in BLM. And then students saw this, yeah, of course, at one, I recognize it. No, 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 be careful, right? X is approaching infinity, not zero. This is only equal to one when X is approaching one, so don't memorize it. Conceptually, feel free to use your microphone. What is the limit?
0.
It has to be 0, right? Think about it, sine theta, it bounces off, right? Back up and down like that. So it's at most it's 1 and at least it's -1, and you're dividing that by very large number. You know what I'm saying? This is not math, but you see why that will give you 0, right? Conceptually. Okay, so can we do this graphically then, right? I have that graph made for you right here, so I'm just going to bring it in. Wow, dang, look at that, right? See, sine x will bounce up and down, but these walls are closing because this is 1 over x and there's a -1 over x. You know what I'm saying? Kind of like in Star Wars Episode 4, that garbage disposal area, they're trapped and then walls are closing on them and eventually it'll squeeze to 0. It may not be exactly equal to 0, but doesn't matter. When we say limit, it means it's not equal to 0 anyway. You know what I'm saying? So, okay, so we can feel it like this. However, how do we justify our feelings? If the test question, AP does this all the time, explain, justify. We have to, one thing is wanting to feel and know the answer, but it's another thing to justify our feelings. So we have to show our work. And it's done this way. This is good old squeeze theorem again. Sine theta is between -1 and +1. We start with 2 known quantities. Good. Then I divide everything by theta, so it becomes this. And this is what I want to know, right? And these two at the end are known quantities. So all I have to do is limit, limit, limit. So limit -1 over theta, theta approaching 0, and less than limit, and then this limit. And then, of course, this thing becomes 0, and this is what I want to know. And this thing becomes 0. So only conclusion we can draw, of course, is this limit of sine theta over theta as that theta approaches infinity is 0. That's how we justify our feelings. Good. So when we say end behavior, it means horizontal asymptote, typically as this is the end, right? Or this end, right? So what value does the function assume? And that's, oh, by the way, you do know that you can cross horizontal asymptote, right? You can cross slant asymptote. Vertical asymptote is the only thing you cannot cross because function doesn't exist there, but everything else, it just means for large x, what value? So what happens in the middle here, we don't care. So that's end behavior. But then question is, well, we have a nice word such as horizontal asymptote. Why do you have to call it end behavior? Why do mathematicians keep coming up with a new vocab? Right, okay. Well, let's see. Do you remember this thing? You remember, was it chapter 1 or 2 of pre-calc? You remember learning this, right? And more importantly, do you remember how to calculate slant asymptote? Right, slant asymptote after doing synthetic division or long division, then you come to see, oh, f of x is cut off. I'm going to write it here. F of x is x squared minus x minus 2 over x minus 1. But if you divide, then you have this and you have that remainder. You know what I'm saying? And this is a very, very nice form. And this is also pretty helpful in order to figure out the x-intercepts. right? But this is, in my opinion, the most helpful form there is. Okay, and then this was your slant asymptote, y is equal to x, is what this thing is, right? Now, my question, you know how to do it. My question is, why is that? Why does that give you slant asymptote? See, you have to know what you're doing. Why is that? Weird, huh? Here is the thing. If you have written a function like this, x minus 2 over x minus 1, so quotient and remainder kind of thing, near the vertical asymptote, if x is near 1, which is a vertical asymptote, which of the two is a dominant term? Let's say x is about 1.1 and try to calculate this. So we have 1.1 minus 2 over 0.1, isn't it? Which of course is 1.1 minus 20. You see, this is a dominant term near the vertical asymptote. You get it? So the behavior near the vertical asymptote, of course, is this. It behaves exactly like this term. How about that, huh? As you can see here, this right here and that right there. Okay, but for large x, say x is approximately 1000. And we'll try to compute this. F of x is then approximately 1000 minus 2 over 999, isn't it? You see why this is a dominant term? So what we have is, for large x, I think more professional term, as x approaches infinity, my function behaves like that function. You get it? That's why this is the asymptote. It approaches that. But you see that it's not exactly equal to, there's a little bit of tiny leftover. And that makes sense because that line is right here and then it's slightly lower. So it's not quite on, it doesn't touch because of this term, leftover term, remainder term. But it has to get closer and closer, and that's exactly what asymptote is. So this also is called the end behavior function, but instead of calling it slant asymptote, we call it end behavior. End behavior function, we'll just say, name it g of x is equal to x. And here's the definition of end behavior function. If you take a limit of the ratio of the two, you're supposed to get 1. Do you see? If you take a ratio of this and that, you get 1. You want me to show you? I could show you. Okay, let's do it. Limit of x approaching infinity of f of x over g of x is equal to limit of x approaching infinity of, I'm going to use this function, this form, right? And then that is limit of x approaching infinity of, we separate the fractions, so we have 1 minus 2 over 2 times x times x minus 1. You get it? And then this is my notation for taking limit. You can use it too. Instead of writing another line, that thing dies. So we have 1. You get it? What that means is for large x, f and g are about the same thing. And that's exactly what asymptotic behavior is. Now, that's nice and great, but it still does not explain why this is called end behavior instead of asymptote. Right? For that, I'm gonna have to, oh, I didn't mean to show you all of this. Okay, pretend that you didn't see that. And then pretend you are not about, oh no, I've seen it already, so too late now. Parabolic asymptote? Do you see a parabola in here? Because in case of the slant asymptote, what we did was I divided second degree function with the first degree function, so our quotient is linear and we have a remainder. That's why we have a linear, right? But if we divide third degree with the first degree, then we'll have a second degree quotient. That's a parabola. No, tell me it ain't so. Parabolic asymptote? Yes. And I have to demonstrate how to do this live. Okay, so it's a cooking show. I cooked this turkey before, so I'll take it out of the oven, but pretend I'm putting a new turkey in. Have you ever watched the cooking show? They have two different ovens, so you stuff it and prepare it, rub it, and then put it into one oven, and then there's another oven. It's like, let's suppose this is 4 hours later, and they take the fully cooked turkey out of the other oven. Yeah, it's kind of like that. So I cooked this turkey during second period, so I'm going to reuse it. So suppose this function, g of x, we'll call it, is x cubed minus 4x squared plus 2x plus 8 over x minus 2. Okay? Now, we're going to have to divide in order to find the asymptote, right? Long or synthetic, your choice. Let's just pick one. Feel free to use your microphone. Synthetic, of course. Like, why would you want to do long? Everybody loves synthetic, right? Unless you forget to put 0 in the middle. I'm going to do it here. So we have 1, -4, 2, 8, and we'll divide that by 2. So we have 1, 2, -2, -4, -2, and -4. So we have 4, and that's the remainder. So this same thingy, we can write it as x squared minus 2x minus 2, and then plus 4 over x minus 2. You know what I'm saying? Okay, so nearby, actually, I'm going to be a little more formal. As x approaches 2 from the right-hand side, which is the dominant term? This, of course, isn't it? But that shoots up to infinity, and this is still a number. You know what I'm saying? So do you see this as positive infinity? That gives you this kind of behavior. By the way, what was your requirement in drawing asymptotes? Was it color? Was it highlighter? Was it combination of the two? What did Miss Slattery require? Because I know what Mrs. Kirk requires. It has to be red pen only. It cannot be purple, it cannot be green, it has to be red pen, right? And then Miss Slattery says, just dotted line is okay, right?
Yeah.
Okay, do you wonder what my requirement is? It's one or the other, either dotted line or color. And you can do purple, you can do green, any color. So it's either color or dotted line, as long as you don't put solid line, but do use a ruler, okay? Do as I say, not as I do. Use a ruler, okay? Lines are straight. Okay, so that's my requirement. So that gives you this end right there, right? Okay, then what about if I take the limit on the other side? Limit of g of x as x approaches 2 from the left-hand side, and looking at that thingy, do you see this is negative infinity? So that gives you, this thing has got cut off. So this thing you will, like that. You get it? Okay, so that takes care of vertical asymptote. Of course, zeros, you're on your own to calculate intercepts. But what is the end behavior function? Well, this is your end behavior function. You get it? So we'll say end behavior here, and we'll call it h of x, which is x squared minus 2x minus 2. Caution, caution. Your idiot book just says that's end behavior. And it fits that definition of taking limit, ratio of the limit, and gives you 1. If you do that, I'm going to take a lot of points. And this is being recorded, so I have a video evidence of warning you like this. No, you have to include all of this. The whole point of doing end behavior is an asymptote. It is to aid us in graphing. So if you use the first one, this is not as accurate. You know what I'm saying? You know they're not the same thing. So don't say, but the book says. You've been warned before. So let's graph this. And this is, of course, x minus 1 square, and is it minus 3? Is it too much algebra? You want me to teach you how to complete the square, or are we good? Okay, let's say we're good. Now, this is an asymptote, so I'm going to use red and graph this. And I taught you the pattern, right? 1, negative 3 is here, and then here, here, and it goes up by 1, 2, 3. And then it goes up by 1, 2, 3, 4, 5. Let's do one more. 1, 2, 3, 4, 5, 6, 7. You see how closely this thing follows? Of course, we are pretending that we cannot see this function yet. Yeah, I cooked this turkey before, so it appears, but. So if you have it like this, then you see it exactly follows our asymptote. Now, but parabolic asymptote, I'm up to slant asymptote, that term asymptote was fine. But parabolic asymptote, but what happens if I put 4th degree function on top? Then we have a cubic asymptote. What happens if I put 5th degree function on the numerator and 2nd degree function? Oh my God, 2 vertical and even there's no end, right? So instead of calling it asymptote, we call it end behavior function now. End behavior meaning for large x, going this way or that way, your function will mimic that end behavior function. You get it? As you can see here, it's following this parabola very closely on those ends. And then in the middle, it's more like a vertical asymptote, this thingy right here. Any questions? Very good.
Mr. Kim, I think there's someone in the lobby.
Oh my God, Andrew Park. Okay, thanks for letting. Andrew, did you get cut off or something?
Oh yeah, I'm so sorry, my internet disconnected.
Oh, okay.
Sorry.
Yeah, alrighty. Are we good? Any questions? Then the question is the end behavior on the right and end behavior on the left always the same? So far they have been saying. Have we ever seen a function with a 2 different horizontal asymptotes? Yes, you have. This thingy, right? What did it look like? It looks like this, right? Negative. Oh my God, huh? So this is your right-hand behavior, and this is your left-hand behavior, isn't it? We have seen it before, you just didn't recognize it. Well then, let me give you this. What happens if our function is this? No, tell me it ain't so. Let's just conceptually think. As x approaches positive infinity, which is a dominant term of the two? Which is bigger number if you plug in numbers?
E to the f.
Right? So this is the right-hand behavior, right? But as x approaching negative infinity, which is the dominant term? You see, e to the x dies, right? E to the negatives, that's exponential decay function. So now it becomes sine x, right? So this is left-hand behavior, isn't it? What? No, you mean there's no way. There's no way, right? Are you a believer? Well, not that one. Oh my God. So we clearly see sine x on the left and e to the x on the right. I'm going to superimpose it with these two and behavior functions. Now this is our function. You see how closely it follows the sine x on this left-hand side and how closely it follows e to the x on the right-hand side. Dang, huh? So left and right and behavior does not have to be same. How about that, huh? Okay, I'm gonna hide all of this for the fifth period and then not accidentally show them. Any questions? Okay, then we are ready to talk about continuity. Okay, for continuity, I'm just going to save time. Go with the notes. Okay, suppose we have this. Okay, I think you know how to graph both of these things, right? So this thingy has discontinuity right here when x is equal to 2, right? Boom, boom. So if you take a limit, the left limit is 5 and the right limit is 1/3. Do you understand this thingy? Left limit and right limit being different? Now we have seen this case before. There's a hole right there, right? In this case, limit exists. Left limit is 2 and right limit is 2. And this function, of course, value of the function, the dot is right here. So there's a tiny little gap right there. This is discontinuity. However, something about these two discontinuity that are fundamentally different. Okay, so we'll classify discontinuity before we move on. Then we are ready for the definition of continuity. So these are the types of discontinuity. First one is continuous. Okay, we are looking at when x is equal to 0, so it's continuous right there. Okay, this is called the removable discontinuity. There's a hole, so it doesn't. The function doesn't exist. F of 0 doesn't exist, but other than that, limit exists, right? Right limit, left limit agrees with each other. I'm gonna look at these guys first. This is what we saw before. Here, f of 0 exists is 2, but it doesn't connect with this. So limit exists here. Left limit, right limit both give you 1, but the value of the function is up there. These are called the removable discontinuity because it's easy to remove it. All you have to do is just take that point and fill it right here. It can be patched up easily. Now, this is known as a jump. Think Super Mario Brothers. Do you remember Super Mario Brothers? When Mario is walking, boom, 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 boing, boom. You get it? He has to jump. In this case, he doesn't have to jump. He can just walk right over because that gap is too small, so it's not going to fall through the crack. You remember the difference between those two? Some things you can walk and some things you have to jump, otherwise you fall between. So this is a jump, and that's a pretty obvious name now, isn't it? This one right here is known as oscillating. It's just like crazy going on right here, but it doesn't really connect. You rarely see this, okay? So it's just like know that it exists. And if you have vertical asymptote, this is known as infinite. You know, the Mario cannot jump over this thing. There's a wall, so he has to go into a pipe and then emerge on the other side. Yeah, that's known as the infinite if you have a vertical asymptote. So these are different type of discontinuities, right? Okay, so I think we understand the definition of continuity now. So layperson's idea of continuity is this: if you can draw it without lifting your pencil, that's continuous. See, right? But. Say we have this. I'm gonna draw it a little differently. Say we have a function like that. Something about this kind. This is when x is equal to c, and of course this is f of c, right? This is known as removable discontinuity, and this fundamentally this type of discontinuity is different than any other like jump or infinite. And the reason is the right limit that one agrees with left limit. That one, right? So we can actually say, putting these two together, limit of f of x as x approaching c is equal to each other, right? But this is not necessarily same as f of c, because f of c in this case does not exist, right? Or f of c might be over here, right? And those are not equal. So that's the only thing. You can just walk over it. It's almost continuous. So what is the only way you can, what is the way you can remove this discontinuity? Right there, you fill that hole. You get it? And this is definition of continuity at point C. If that happens, then we say f is continuous at x is equal to c. Good? Now, say this point, this is like axis right here. This point is A, point A, and this point is B. Right? For every point, every number C in between, if f is continuous, if f is continuous for all C that is within A and B, then we say f is continuous on interval A and B. How about that? Kind of like standard, pretty obvious definition. When we say f function is continuous within the interval, that means it's got to be continuous everywhere between those two. Good? And this is a biggie, definition of continuity. Look at number 17 first. Okay, number 17 looks like this. I'm gonna do it with red. So if you have a limit of, we have to understand what this thing is. As x approaching 0 from the right hand side. See, whenever you have this thingy, and then if you put in, let's say you put 0.1, do you see it gives you 0? But if you put in negative 0.1, this gives you negative 1. It always gives you the integer on its left. You guys are familiar with this thing? Okay, so if as long as x is greater than 0, so it's like 0.00001, this is 0. You know what I'm saying? But at the same time, if we take this limit and x is approaching 0 from the left hand side, this will be negative 1 with the same reason. Are we good with that? Now we are ready to do this problem. So if I do this, as x approaching 0 from the right hand side, the numerator becomes 0, right? Numerator becomes 0. Denominator is becoming 0, but still, when we say limit, it means it's not equal to. And that greatest integer function itself returns 0. So this is already set to be 0. So that thing is 0. You know what I'm saying? However, if we do this, by the way, does the book call it INT? INT is exactly this in the calc. And then that one, since x is negative 0.0001 thing, is set to be negative 1. And then we have this. And x is approaching 0, right? And x is technically a little negative. So that's why we get negative, negative, negative infinity. How about that? You get it? Okay, Thai.
I had like a general question for number 7, letter C. It says that there are 2 horizontal asymptotes, but for that one the graph goes over, like it's a horizontal line that goes over those asymptotes. So how is it an asymptote if the graph like touches it, I guess?
Okay, you can cross horizontal asymptote as many times as you want to, and this is a classic example. Okay. Let me put it on the screen. Like that. I need a new one. Let's go back to this example. We have seen this example before, right? Now, is this x-axis our asymptote? Yeah, it is. It just converges to this line, but it crosses the asymptote infinitely many times. You see that? So yeah, this is because vertical asymptote is the only thing you may not cross. Horizontal, slant, parabolic, you may cross any of those things as many times as you want. You get it? Okay, next question.
Number 43.
43. Let's look at 43. I should have taken and lined up all these questions. I'm gonna have to open the book and get it. Are we on chapter 2? Yeah, we are. Okay, what section are we on?
2.2.
40. Opening this electronic book is not as easy. But I think I'm almost there. Did you say 3 or 2?
43.
43. Okay. Let me make a copy. So we are just finding the end behavior function, right?
Yeah.
So when we have this, all we do is just do a division. You guys prefer synthetic, right? You want long? Your choice. Make up your mind quick.
Synthetic.
Okay, x squared, and this is x, and this is 1 and 2. So we have 4, 8, 8, 16, 14, 28, and 29, right? So that same f of x can be written as 4x squared plus 8x plus 14 plus 29 over x minus 2. So our end behavior function happens to be just this part. I know your idiot book only put that thing in, but that's not right. This whole thing is your end behavior function. And since we are not graphing it, we don't have to complete the square or anything, right?
Wait, so I did that, and then the book said just to take the first term.
I know, I just said your idiot book only puts this as an answer, right? That is not correct. Don't do it. I take a lot of points if you do that, okay? List the whole thing, everything, okay?
So if it's like just a polynomial, like say the function with just the g of x1, would the end behavior function just be the same? Okay.
Yeah, polynomials, of course, have exactly same end behavior. Why wouldn't it, right? Okay, any other question?
How do you graph 33?
33? Okay, let me look at 33. Oh, that's just a secant x, isn't it?
Yeah, but I think when I used the graphing calculator, it was just like a straight line.
Oh, see, that should, you should be able to do it without calculator very accurately. That's all last year's curriculum. I mean, you should have endless tests on that.
So is it just secant of x?
Yeah, because let me write it here. 33. C f of x is equal to tangent x over sine x, but tangent x is sine x over cosine x, isn't it? And then divide by sine x, and then these two cancel. Ooh, why is it acting weirdly? So it's 1 over cosine x, which happens to be secant x. How about that? Okay. Okay, any other question? Oh, well, I should go by the order. Brenna.
Could you go over 41?
Okay, 41 is just 0, but let me do it here. So if you want to take a limit of x minus 2 over 2x squared plus 3x minus 5, right? As x approaching infinity or negative infinity gives you the same thing in this case. And then you see your denominator grows faster than numerator, so denominator wins. So this is, and then if you want to show your work, you divide everything by this thingy, x squared. So you have 2 plus 3 over x minus 5 over x squared here, and then you have 1 over x minus 2 over x squared. Now if you take limits, this dies, this dies, this dies, this dies, so you have 0 over 2, which is 0. How about that? You get it?
Thank you.
Next question. Oh, wait. Next one. Daniel.
Could you do 23, please?
23. We'll look at 23. 23. We are taking limit of cosine 1 over x over 1 plus 1 over x, right? And then x is approaching infinity. Now, I'm going to make a little substitution. Okay, if I do, this thing now becomes cosine theta over 1 plus theta. So far so good? And then if x approaches infinity, theta will approach 0, correct? Now let's think about this. We just plug it in now. So cosine 0 is 1 and 1 plus 0, right? This is theta. How about that?
Thank you.
Reese.
Can we do number 47?
47. Let's look at 47. 47 is, well, I'm gonna put that.
Felt, but how do you do the limit?
Yeah. Oh, so you felt the graph, or you seen my graph. I'm gonna still make a copy of it and put it here so we can look at it together. So this is what it looks like. And then I will do the limit. So certainly best we can do is this line, right? Which is just this, right? Okay. Now we ask ourselves, as x approaches infinity, which of the two is the dominant function? And ln grows very slowly. So we see that x is the dominant function, right? Okay, so if we do, so we suspect this thingy, our end behavior is x. And if we take a limit of this, x approaching infinity, now we can 1 plus, now we can drop the absolute value since this is positive infinity, it becomes this. Now, question is, how do you know this approaches 0, right? In order to analyze this, we need chapter 8, but then we are in chapter 2. So you'll have to trust me for now, but x grows so much faster than ln x. Ln x is one of the slower growing function now, isn't it? That versus this, right? You see that gap is huge. And then, of course, denominator wins, so that just becomes 0. When we get to chapter 8, I will be able to prove this to you, okay? But that's the best I can do at the moment. Any other question? Oh, wait.
Yes.
Ixion, or also known as...
Yeah. Yeah, I go by Sarah, but like I have two questions. So the first one, do we consider negative or positive infinity as limit, or do we just say that they doesn't exist? Because I think in group we kind of say that.
Oh, okay. When you say the limit doesn't exist, that's a bigger set. Limit does not exist. And technical term here, really mathematical term, is divergent. Okay? Inside the divergent limit, there are subsets, and these are plus or minus infinity and oscillate. And then there are like a bunch of others in it. So when you say infinity, that really means divergent or does not exist. But it's more specific type of divergent. You know what I'm saying? So in a way, they are both correct. You know, the square is a rectangle. So you can say rectangle, square. If something is a rectangle, you can say yes, it's a rectangle, or you can say yes, it's a square, which means it's a rectangle. You get it? And your other question?
Yeah, thank you. So my other question is about number 33. So the way the textbook describes the asymptotes, I wonder how can we get that answer?
You just have to know what it looks like. But one way to think about, we had a 33, so we'll go back to 33, right? It's 1 over cosine x. So whenever the denominator becomes 0, there's an asymptote, right?
Mhm.
You're asking yourself when is cosine x equal to 0? Well, pi over 2, 3 pi over 2, so on. How's that? Oh,
Yeah, but I think the textbook is like described as using two different situations. So it says that like A equals parenthesis 4k plus 1 parenthesis pi over 2, and there's another B equals 4k plus 3 parenthesis times pi over 2. So I wonder if we are required to write that kind of expression to kind of.
it means the same thing, but I would do this, what you were taught last year, pi over 2 plus k pi, right?
Yeah.
That means exactly the same thing.
Yeah, but I mean, like, if we do that, it'll be really hard for us to describe the end behaviors, not the behaviors near each asymptote, like from the left and right side.
Yeah.
Because,
This is like plus or minus infinity. How's that? I'll take that.
well, do we need to specify which one is left and which one is right?
Unless I ask of you. So yeah, you can see. I'm gonna put that graph here. And if I zoom in a little bit, you see this side goes up and this side goes down. That you get it from graphing, and you should know what that looks like. So if my specific question is approaching pi over 2 from the left, you do have to put positive infinity as opposed to this one, negative infinity.
Okay, thank you, I see. So in the test, it will just be the behaviors near a specified asymptote, but not all of the asymptotes.
No,